Good morning, class. Gonna wait for a couple more viewers. We're going backwards. All right, I think I'm gonna go ahead and start. All right, good morning, class. I just want to remind you about the midterm, which is due on Wednesday at 11:59 p.m. And as of now, 0 people in my AP Physics 1 class have taken the midterm. So, in fact, out of all my classes, only 2 students have taken the midterm as of yesterday when I checked. So that's a little bit concerning. So I don't know. I just don't want you to feel too much pressure while you take it. All right, so this is going to be our last forces lecture today. If we were having a normal school year, we would probably spend a bit more time on forces, but I'm kind of picking the essential things that you need to know about forces. And maybe if later in the school year we go back to class in person, we'll be doing some labs and stuff that will come back to forces, okay? So the topic of today's lesson is called Multipart Systems. All right. So up to this point, we've been interested in the motion of a single thing. For example, a block or a box, okay? Multipart systems have 2 or more things with different masses, and so it's interested in what is the motion of each of those things and how are they interacting with each other, okay? So this is just kind of an introduction to that. And so our first example is going to be what's called an Atwood machine. Okay. So an Atwood machine has, I don't know, there's a ceiling and there's a pulley that is hanging from the ceiling. So if you don't know what a pulley is, it's basically a cylinder that can rotate, and it has grooves where you can put a rope over the top of the pulley. So there's a rope. And then on either end of the rope, there are some masses. Okay, so this is kind of a classic example of a multi-part system. And we're just going to say for this problem, we're going to say that this is a 2 kilogram mass and a 1 kilogram mass. All right. And then maybe there's a floor down here, but the masses are not touching the floor. All right. Now, there are a couple of things I need to talk about before we solve this problem. The first one is to talk about ropes a little bit. So the force from a rope is called tension. The force from a rope is called tension, which is denoted by T. Okay, and the tension at each end of the rope is the same. All right, so if, for example, this rope right here is pulling up on the 2 kilogram mass with some tension T, that same tension is going to be pulling upward on the 1 kilogram mass, okay? So the tension at one end of the rope is the same as the tension at the other end of the rope. If you have a problem where there are 2 ropes or 3 ropes or however many ropes there are, each rope kind of has its own tension. So the tension isn't the same between 2 different ropes, but if you have a single rope, the tension at either end is the same. Okay. Furthermore, in this system, in these types of systems, the magnitude. So magnitude means the size, not worrying about direction. The magnitude of the accelerations are the same. Okay? The magnitude of the accelerations are the same. So why is that true? Well, let's imagine a situation. I think it's fairly obvious that because the 2 kilogram mass is heavier than the 1 kilogram mass, that if this system starts at rest, the 2 kilogram mass will fall, the 1 kilogram mass will rise, okay? So let's assume that the 2 kilogram mass falls 1 meter in 1 second. Then because this, assuming it's not like a stretchy rope, so if the 2 kilogram mass falls 1 meter in 1 second, then the 1 kilogram mass is going to rise 1 meter in 1 second. So that means that their position time graphs are going to look the same. And if their position time graphs look the same, then that means their velocity time graphs are going to look the same, which means they're going to have the same acceleration, okay? But the thing is that this 2 kilogram mass is going to accelerate downward, and the 1 kilogram mass is going to accelerate upward. All right. Oh my gosh. So, okay. So we're not going to have an A1 and an A2. Okay. Not going to do that. We're just going to have the system has a single acceleration A because of the rope connecting the two. What we're going to do, and this is one of the few types of problems where we're going to have downward being positive in some cases. Okay. So what we're going to do is we are going to choose a positive direction. Oh my gosh, you said nap, and then I didn't sleep very well last night. You need to choose a positive direction. So, and I woke up really early yesterday because it was going to be so hot. I decided I would wake up at 5 a.m. and I went for a run before I taught my classes, and then I went to bed late on last night as well. So, running on low sleep. I'm going to choose a positive sense for this problem. Okay? So that I like to choose the positive sense to be the sense in which the system is going to move. Okay? So I know that the 1 kilogram mass is going to rise, the 2 kilogram mass is going to fall. So this is the sense of the system. Okay? So what that means is, so this is kind of like the pulley is going to rotate clockwise. So that means that downward is going to be the positive direction for this mass on the right, and upward is going to be positive for this mass on the left. Okay? So this is a rare case where downward can be positive, where we would choose downward to be positive. Let's do a free body diagram for each of these masses, okay? So I'm going to have, for each of these masses, for the 2 kilogram, it has tension pulling it up, okay? And it has weight force pulling it down. So the weight force is going to be m times g, 2 times 10, 20 newtons. Okay? Notice how I'm drawing this isn't so important for all the time, but sometimes we want to make a free body diagram where the sizes of the arrows are accurate. And in this case, I am going to do that. And we can see that I've drawn the 20 Newton arrow to be longer than the tension arrow. And the reason is that I know that the 2 kilogram mass is going to fall. It's going to accelerate downward. And so I had better have more downward force than upward force. Okay? Then I have, for the 1 kilogram mass, I have a tension going upward. And these two forces should have the same size because the tension on one end of the rope is the same as the tension at the other end of the rope. Okay? So you've got this kind of a situation here. And then this one has a weight force, which is 10 newtons. All right, m times g, 1 times 10. And notice how I've drawn the 10 newtons to be shorter than the tension because I know that for the 1 kilogram mass, it's going to accelerate upward. So I had better have more upward force than downward force. Okay? So here's how we're going to solve the problem. We are going to write Newton's second law. But Newton's second law applies to each mass. okay? Just like for all of the atoms in your body, Newton's second law applies to each of those atoms separately, okay? So that would be a really multi-part system because you have, moles and moles of atoms in your body. So that's a lot of Newton's second laws that you have to worry about. Nature figures all that out, okay? So I'm going to write Newton's second law for the 2 kilogram mass. And I'm going to write Newton's second law for the 1 kilogram mass. Okay? So for the 2 kilogram mass, it has a 20 Newton downward force and tension going upward. The tension is unknown. So I'm going to have 20 minus T equals MA. So 2A. All right? Now you might ask the question, well, isn't tension going upward? So shouldn't that be the positive force? But this is one of the rare cases where C for the 2 kilogram mass, downward is the positive direction, okay? So whatever direction you choose to be the positive direction, you know what I mean? So I said in a previous lecture that most of the time the net force in the y direction is up forces minus down forces. That would be in a situation where we chose upward to be positive. If we choose downward to be positive, then the net force in the y direction is going to be down forces minus up forces, okay? So now let's look at the 1 kilogram mass. The 1 kilogram mass has upward as the positive direction. So its net force is going to be up force minus down force, T minus 10. And that equals MA, so 1A. So we've written 2 Newton's second laws for 2 different masses. Okay? And for one of the masses, upward was positive, and for the other one, downward was positive. Notice how I only have one tension variable because the tension at one end of the rope is the same as the tension at the other end of the rope. Oh my gosh. And also, I only have one acceleration variable because the magnitudes of the acceleration are the same. All right? So this is an example of what in your math class you would call a system of equations. Okay, do you ever solve those problems in math class where you have like 3x plus 2y equals 4 and minus 2x plus 8y equals 7? And you have to solve for x and y based on those two equations. This is the same kind of thing. Okay? So we add these two equations together. This is a very easy, simple, it's a very simple system of equations to solve, okay? And so what you want to do is you want to add the two equations together, all right? Why is this the thing you want to do to solve the equations? Because when you add them together, because the tensions were the same, you have a minus t here and you have a plus t here. So these two are going to cancel out when you add them together, okay? So those two cancel out, and the 20 and the 10 are what is left over, and you have 20 minus 10 on the left-hand side of the equation. So we've eliminated tension. On the right-hand side, okay, we have 2a plus 1a, which is going to be 3a. All right? So I'm going to carry out the math to solve for the acceleration. And if you know the answer, type it into the chat how, like let's say you're solving a system of equations and you solve for x. You know the number that x is going to be equal to. How do you then figure out what y is in a system of equations? Okay? So type that into the chat if you know the answer. So on the left-hand side, I have 20 minus 10, which is 10. On the right-hand side, I have 3a, divide both sides by 3, and I can see that the acceleration is going to be 3.3 meters per second squared. Okay? So what does that mean? It means that the 2 kilogram mass is going to accelerate downward at 3.3 meters per second squared. The 1 kilogram mass is going to accelerate upward at 3.3 meters per second squared. All right? So excellent. I see that you know how to solve system of equations. So you plug your value for x into one of the two equations. You can actually plug it into both equations, and you should get the same answer. Okay. So that is a great way to check that you have solved the system of equations correctly, is to plug this into both equations. Okay, so I'm not going to do that generally, but I will do that for this problem only, just because I want to show you how that would work. But you know, I've been doing physics long enough that that I am confident that I have the answer correct, and so I would generally only plug it into one of the two equations. Okay, so let's say I plugged the acceleration into the top equation. So that would be 20 minus t equals 2 times 3.3. So that means that 20 minus t is equal to 6.6. So that means t is equal to 20 minus 6.6 equals 13.3 newtons is the tension in the rope. Okay? What if I had plugged the acceleration into the bottom equation? T minus 10 equals 1 times 3.3. So then I add 10 to the other side, and I get 10 plus 3.3, which is 13.3. So see how it didn't matter which equation I used, I got the same answer. All right, and so that is proof positive that you have done the problem correctly. So if you are unsure about an answer, that's what I would recommend you do. All right, let's do some more. More examples. So let's suppose you have a table. Here are the legs of the table. Oh, you know what? I forgot to ask a question. Why is it that in these free body diagrams I did not include the normal force? Okay? Type it into the chat if you know why I don't have the normal force in this Atwood machine problem. Okay, so you have a table. Table is sitting on the floor. The table has a pulley on the end of it, and there's a mass that is sitting on the table. Let's make this a 3 kilogram mass. And then there is a also a 3 kilogram mass that is dangling, and these two are connected by a rope. There is a coefficient of kinetic friction, which is equal to 0.2 between the table and the block. Okay. So I see some responses. I don't know why there's an individual who typed into the chat who is not in this class. Get out of here, Miss Zhao. Just notice that. Yeah, exactly. So there's some good answers in the chat to my question, which is that the blocks are not touching the ground. Okay, so the normal force is a force of contact. There needs to be contact between two things in order to have a normal force. So if these masses are just dangling, there's not going to be a normal force. Okay. If we go back to this example, this mass is going to have no normal force because it's dangling. This mass is going to have a normal force because it's on the table. It's in contact with the table. Okay. So, a lot of times in physics, what we do is we represent things by blocks and pulleys and things like that. But really, this is quite a general scenario. So let me give you a scenario where this type of problem, you could do the exact same math for a more complicated sounding scenario. What if you were mountaineering, okay, and you and your partner are climbing the mountain. Your partner falls off the edge of the trail or the mountain or wherever you are, okay? And you are still on the mountain. You guys are connected by a rope for safety, and you're trying to arrest the fall of your partner, okay? So we could model that situation as two masses connected by a rope. One of the masses is dangling, and there's friction, okay? So that friction is basically representing the amount of traction that your climbing shoes have in the snow or the ice or whatever it is, okay? So I encourage you to even though I might do some problems where it's just blocks and pulleys and things, these are really just models for more realistic scenarios, okay? So I think it's fairly... All right, Miss Zhao is being defiant. She's being defiant, so if we were in person, I would write her a detention. So anyways, in this case, the amount of traction is not going to be enough to arrest the fall. So actually, this 3 kilogram person is going to drag the other 3 kilogram person off the mountain with them. And so I'm going to choose this to be the positive direction. So the positive direction for the dangling mass is going to be downward, and the positive direction for the table mass is going to be to the right, okay? Because if the 3 kilogram mass falls by 1 meter, the dangling mass falls by 1 meter, the table mass moves to the right by 1 meter, okay? So this is a case where I'm going to draw the free body diagrams, okay? So for the dangling mass, it is extremely simple. We just have a weight force of 30 newtons going downward, and we have a tension force going upward, okay? All right. And the 30 Newton force is going to be the positive force. For the table mass, we are going to have the normal force is going upward. We're going to have tension going to the right. Because this mass would tend to slide to the right, that means that kinetic friction is going to point to the left. And then it has, again, a 30 Newton weight force going down. Okay? Now, because this table mass is not jumping off the table or crushing through the table, we had better have normal force equals 30 newtons. Okay? If those two forces were not in balance, then the mass would accelerate up or down. So that means that my normal force is 30 newtons. Okay? And if you recall from previous lessons, the normal force is what allows us to calculate the amount of friction, either the maximum static friction or, in this case, the actual value of the kinetic friction. So the formula for kinetic friction is mu sub k times normal. So that's going to be 0.2 times 30, which is 6 newtons. Okay? So I know that this is 6 newtons. I also know that because this is the same rope, that these two tensions are going to be the same. So I kind of use the same notation as you might have used in when you were learning geometry, which is, in geometry, when two things are the same, they might put a little slash on them. So these slashes indicate that normal force is equal to weight force, and then but the tension is not equal to the normal force, so I have to use a different indicator. So I use two slashes to indicate that these two tensions are the same. Okay? All right, so that was a little bit trickier because I had to look at a full free body diagram and do that analysis to get the friction force. So now I'm ready to write my system of equations. So I have net force equals ma, and I'm going to write that for the dangling mass, and I'm going to write that for the table mass. So for the dangling mass, we have a downward force of 30 and an upward force of t. So the downward force is the positive direction for this particular problem. So 30 minus tension equals 3a. Okay. For the table mass, the table, the positive direction is to the right. Okay. The negative direction is to the left. So we're not even going to worry about friction and weight force because those forces are perpendicular to the direction of motion. So I can just, the only purpose that they served in this problem was to allow me to calculate friction. Okay? So they kind of enter into the problem indirectly. So for the table mass, the positive direction is the rightward direction, so I have t minus 6. Tension minus friction, and that equals 3a. Okay? So just like last time, you want to add your two systems of equations. Okay? So adding them, I have a plus t and a minus t that they're going to cancel out. And then I have a 30 minus 6, which is 24. And that equals 3a plus 3a is 6a. Divide both sides by 6. And we get that the acceleration is 4 meters per second squared. Meaning that the 3 kilogram mass is going to accelerate downward at 4 meters per second squared. And the table mass is going to accelerate rightward at 4 meters per second squared. All right? So while if we go back to our mountaineering analogy, while the fall was not arrested by the person who was still on the mountain, the person on the mountain did reduce the acceleration. So if this person does hit the ground, they're going to hit the ground at a lower speed than they would otherwise. Okay? We could actually calculate that if we then fed this acceleration into a kinematics equation. The next thing I want to do is I want to calculate the tension. So I'm going to plug it into the table equation. So I have T minus 6 equals 3 times 4. So T minus 6 equals 12. Adding the 6 to the other side gives a tension in the rope of 18 newtons. Okay. Another thing that we could talk about that I haven't really mentioned before is ropes have different ratings, which are the maximum tension that the rope can support without it's the maximum tension that the rope can support without breaking. Okay, so if, for example, the rope had a maximum tension of 10 newtons, then what we do is we assume that the rope can support the tension. We calculate what the tension would be. So in this case, the tension would be 18 newtons. And then we compare that to the maximum tension that the rope can withstand. And so because 18 is greater than 10, we could conclude that the rope would break and that the person would then fall at, and have a downward acceleration of 10 meters per second squared. So you can kind of, again, you can see whether this situation would be safe or how close is the tension to the critical tension that would cause the rope to break. Can do kind of a safety analysis, which is cool. There's a question in the chat about, can you explain why it is 30 minus t for the net force? So for this dangling mass, downward is positive. Okay, so it has a tension going upward, and it has a 30 Newton weight force going downward. There's no normal force because it's dangling, it's not touching the ground, at least not yet. And so because downward is positive, the net force is going to be down forces minus up forces. So we have 30 minus t. Okay? So we're going to do one more example here. And so what I want to do with this example is show you how would you analyze this with if there were three masses. Okay? So what if we had a table, and that table has two pulleys, one on each end. And then we have, this is going to be a frictionless table, a smooth table, so friction is not going to play a role. And we've got a dangling mass on either side. Okay, and then we have a mass in the middle that is on the table. Let me give these some numbers. Let's say that maybe this is 2 kilograms. Maybe this is maybe 1 kilogram. And maybe this is also 1 kilogram. Okay? So for this problem, I am going to choose this to be the positive direction. Why? Because I know that this 2 kilogram mass is sort of competing against the 1 kilogram mass for which way the system is going to move. And the 2 kilogram is bigger, so I know that the 2 kilogram is going to fall, the 1 kilogram is going to rise, and this 1 kilogram is going to move to the right. Okay? So all three of these have different positive directions. The 2 kilogram has a positive direction that is downward. The table mass has a positive direction that's to the right. And the 1 kilogram dangling mass has a positive direction that is upward. Also, this problem has two ropes. Okay? this is not a single rope. It's two ropes. Okay, there's a rope connecting 2 kilogram to the table mass, and there's a rope connecting 1 kilogram to the table mass. All right, so that means I'm going to have two different tensions in this problem. So I'll call that rope number 2, and I'll call that rope number 1. Okay. So we are going to do Newton's second law, but this time we're not going to have 2 rows of equations. We're going to have 3 rows of equations because Newton's second law is true for each mass. Okay. So we have net force equals ma, and we've got it for the 2 kilogram mass. We've got Newton's second law for the 1 kilogram table mass, and we've got a Newton's second law for the 1 kilogram dangling mass. Okay. So for the 2 kilogram mass, downward is positive, so it has a positive 20 Newton weight force, 2 times 10. It has a negative tension from rope number 2, so we have minus T2, and that would equal 2A. All right. For the 1 kilogram dangling mass, here comes the yawn again. For the 1 kilogram dangling mass, upward is positive, and so we have tension 1 is in the positive direction, and there's a 10 Newton weight force in the negative direction, and that equals 1A. The table mass is a little bit trickier because the only side-to-side forces it has are tensions. So there are 2 tensions competing against each other. Rightward being positive, so there's T2 is pulling it to the right, and T1 is pulling it to the left. Okay. If we had had friction as well, then we would also have like a minus friction. Okay, but we don't have friction, so I'm not going to worry about that. So that equals 1A. So now I add all 3 equations together. Okay, and the math works out exactly the same because here we have negative T2 and plus T2, so those cancel. And here we have negative T1 and plus T1, so those cancel. So all we have is 20 and negative 10, giving a net force of 10 newtons. And then on the right-hand side, 2A plus 1A is 4A. Divide by 4 on both sides, we get 2.5 meters per second squared equals acceleration. Okay. I will get the tension in each rope. While we're solving this, I always like to do little sanity checks to make sure, does this answer make sense? Okay. A great example of that would be the acceleration always is going to be smaller than gravity in this type of a problem because gravity is the thing that is driving the acceleration. Okay. So you could never get an acceleration of greater than 10 meters per second squared because it's just gravity. Okay. And gravity causes an acceleration of 10 meters per second squared. Another thing is, once I solve for the tensions, I had better have that tension 2 is bigger than tension 1 because the net force on this 1 kilogram mass had better pull it to the right. Okay? So let's go ahead and plug this back in. I'm going to plug into the bottom equation, and I'm going to plug into the top equation. So if we go to the top equation, I have 20 minus T2 equals 2 times 2.5. All right. 2 times 2.5 is 5. So that says, yeah, D represents dangling. So 20 minus 5 would give T2 equals 15 newtons. Okay. Plugging into the bottom equation, we have T1 minus 10 equals 1 times 2.5. So that says that T1 equals 12.5 newtons. So we can see that it is as expected. Okay, T2 is bigger than T1. So that's basically the lesson. I did want to say one more thing though, which is it is possible to have these multi-part systems questions where it is not obvious which direction the system is going to move. Okay, so therefore it's not obvious which direction friction is going to point. Similarly, if we have a problem where there's static friction and kinetic, there could be static friction or kinetic friction. You could get a scenario where you're not sure if the system will move at all. Okay, so you can have these sort of confusing problems where you're not sure what exactly is going to happen, and in that case, what you have to do is you just have to make a guess. You have to say, I think the system is going to move this way, or I think the system is not going to move at all, and you analyze the problem with that assumption, and if you don't reach any contradictions, then your guess was correct. Okay, but if you find a contradiction in your solution somewhere, then that just means you guessed wrong, and you have to make another assumption about the motion of the system and solve the problem again, and maybe that leads to a contradiction. So you have to make another guess about. So it can get kind of complicated, but I just wanted to let you know that I'm not going to ask you that type of problem where it's going to be obvious every time which way the system is going to move. Okay? So that's my lesson for today, and I will see you in the Zoom room.